and then we call this phase. So this is magnitude, and this is the phase angle. Okay, one more suggestion, guys. I think Ali was mentioned last time. See, I post my notes on the course website, and then some of you use electronic notebook, and you annotate, and then scribe it. You just write all my notes plus what you annotate and what we go through in class. Some of you do not have, may not have electronic notebook. What you can do, I am going to post all my notes. As I said that I actually prepared whole summer, prepared for this course for whole summer. And I made some notes already, and I'm going to post all those notes. You can print the physical copy of my notes, and then you can annotate there. Then you don't have to redraw the circuit diagram in class. But you go home, then you actually rewrite all the notes, including the annotation, and submit the study, if that works for you. Is that clear? Okay. So as part of that plan, I have posted my notes in module 2 section of the course website. Is that clear? So I will not go through this background information. You did that already in 240 or circuit theory class, AC circuit and system. So just to remind you that we will be dealing with this impedance. For example, impedance of resistance R is simply R. Impedance of inductance L is simply J omega L. And J omega L, because we will be dealing with sinusoidal signal, steady state signal, so it is simply SL. And S equals J omega. Okay? Impedance of a capacitor with capacitance C is simply GC equals 1 over SC, and S equals J omega. Okay? So that's what we will be using. And it's very easy. Yeah, you will see. So let's go through this example. In this example, we have this input signal, which is sinusoidal. Sinusoidal signal. So we have a resistance, and we will take the output across this capacitor. I will go through all these steps, okay? I will go through all these steps. But before I do these steps, you just try to see what we are looking for, output first. That way, it's easier for you. Those who have AutoCAD PSpice, I'm sorry, but not all the computers functioning. I'm going to notify laboratory and see if you can fix it. But some of you may have AutoCAD PSpice working, so you may want to open it up. So what we are going to see, we are going to provide this input. This input equals pi cosine 20 pi t. What is the frequency, guys? 5 cosine 20 pi t. What is the physical frequency here? 10 hertz. Okay, angular frequency is 25. Angular frequency omega equals 25. 20 pi, what is the unit? Radians per second. And physical frequency F, actually 25. Physical frequency F equals 10 hertz. And because this is the first sinusoidal component, I'm going to call it F1 omega 1. For this part, F2 equals 100 hertz. And for this part, what is F3? 1 1000 hertz or 1 kilohertz. Okay. The maximum frequency is F max is 1000 hertz. Okay, and we have, when you put this in your calculator, how much is it ohm? We have R equals 1000 over 2 pi. How much is it? 1000 over 2 pi. How much is it? $159. Approximately, we will have some fraction, 159. And we have C equals 10 microfarad, which is 10 times 10 to the negative 6 farad. Okay? And we want to see what is the, how does the output look like. Is that clear? What is the objective? I will go through all these steps in a moment. Is that clear? Objective is clear? Okay. So software, if you know the theory properly, how it works, then working with software is a piece of cake. So this is the first time I'm also learning OrCAD PSpice. I use MATLAB Simulink mainly. So I will be learning with you guys. So I go to start, all, cadence, PCB 22. Again, you, oh, sorry, I forgot to stop here. Alright guys, we will be simulating this circuit using OrCAD PSpice. So I went to, we have the input signal. The input signal will be sinusoidal, and the input will be summation of these three sinusoidal components: 5 cosine 20 pi t, 5 cosine 200 pi t, 5 cosine 2000 pi t. So frequency component, the frequency of the first sinusoidal component is 10 Hz, physical frequency, and physical frequency of the second sinusoidal component is 100 Hz, and frequency of the third sinusoidal component is 1000 Hz. So let's see what is the output. How does the output look like? So I'm going to open OrCAD PSpice. So you go to start, and then all, capture CIS 2020. So I'm going to create the schematic completely from scratch. And then I am going to choose a different directory. So EC303, and I'm going to use OrCAD DSpice lecture. In this directory, I'm going to create a schematic. I'm going to give a name. I'm going to call it RC underscore low pass filter. Okay. And then create a blank project. Okay. This is where we will be drawing our circuit. So for that, what we do, we are going to place parts. B. Now we have bunch of libraries, RC, resistance and capacitance. They are in analog libraries, and source, sinusoidal source, sinusoidal signal. All the sources, voltage sources would be under source library. So these are libraries. Here, list of parts. So I'm going to select all the libraries. Here I'm going to search for resistance. So see, resistance R in analog library. So I'm going to double click and I'm going to paste it right here. Escape. And then I need a capacitor. I'm going to paste it. I'm going to place it right here. Escape. Now each component here, R and C, these components have each of these components. How many terminals? 2 terminals. Very important. Otherwise you will get confused. So this terminal. So do you see, if you just place a cursor right here, it actually shows this is terminal 1 and this is terminal 2. And for capacitor, this is terminal 1, this is terminal 2. So capacitor, I'm going to rotate it. So if we rotate, this is terminal 2, this is terminal 1. I'm going to rotate one more time. Now this is terminal 1, this is terminal 2. Okay. And then I'm going to move this label to the left. And I need source. So what you do, you will see that under source library, you can actually explode here. You see that there is a sine component here. So double click and place it right here. Now, this source has 4 parameters: V offset, amplitude, frequency, and AC. AC component is usually used for plotting the frequency response, but sinusoidal component mainly would be described by amplitude and frequency. So amplitude, I'm going to double click here, and I'm going to, what is the amplitude of our first sinusoidal component? Right? So amplitude here is 5 volt. Okay. And frequency is 10 hertz. So frequency, I'm going to double click and I'm going to write down here 10. So using these two parameters, the way sinusoidal signal is defined is as follows. So we defined signal as follows. So this is 5 and this is -5, and then frequency f equals 10 hertz. So VI basically VIT is basically 5 sine 20 pi t. That is the signal, mathematical expression of the signal. Is that clear? However, our first component of the input signal is 5 cosine of 20 pi t, right? So what we have to do, we have to just make a phase difference of 90 degrees. That becomes a cosine signal. So what we do, we go right here and then double click here to see the property editor. And initially, if you don't see all the parameters, parameter table like this, initially you might see like this. In that case, you don't see all the parameters. So what I would suggest that you click pivot, then in that case, you see all the parameters as such. Now, do you see somewhere phase here, right? Phase is currently 0. Make it 90 degrees. Make it 90 degrees. Now, if you simply close the property editor, yes, it will take into effect right here. So it is now cosine signal. Now offset, because our signal starting right from 0 and it is oscillating around this x-axis. There is no offset. So if there is any offset, so in that case, this whole signal could be up or down. So offset is currently 0. Offset is currently 0. You guys are okay? You guys follow me? Okay. Now AC, because we will be simulating, we want to see the output in time domain. So AC part, not in frequency domain, AC part, I'm just going to place it 0 for the moment. Now we have defined our first source. How many sinusoidal components we have? 3 sinusoidal components. Now 3 sinusoidal components are added together. So how do you add the voltage sources? So if you have one voltage source, positive, negative, V1. Now if you have another voltage source, positive, negative, V2, positive terminal of V2, if you connect positive terminal of V2 to the negative terminal of V1, okay, the voltage between these two terminals would be VI equals V1 plus V2. Similarly, if you want to have 3 sources, you just connect them in series. Is that clear, guys? Crystal clear? All right. I am going to use exactly the same principle for adding our sinusoidal components. Is that clear? If you are not able to follow me, please raise your hand. I will turn myself down. Okay, I will stop. I'll go through this slowly. So now I'm going to select this, copy, paste, copy, Ctrl C, Ctrl V. Now it's time to connect all these components with wires. So W for wiring. So let's not this right here. Let's not this right here. Wire W. Okay, we need a ground. We need a ground. To add a ground, press G, and you'll see the symbol 0. So simply click OK. Place right here. Escape. Wire. That's it. Again W just to end. Wire. Oh, by the way, resistance here is 1 here. What was the resistance in our examples? What was the resistance in our example? 1? 59. What was the capacitance for our example? 10 microfarad. So you simply write 10 U. So that is going to be 10 microfarad. So we have configured all the sources, and all these sources will be added together and create an input VI in our case, and it is going to be this is yes.
Why are all the frequencies for the power supplies the same? Or like in the in your PSpice, all the frequencies are 10. That's what you have it as currently.
Okay. Oh, wonderful. That's a good catch. That's a good catch. So now, here, all the frequencies are 10, so we have to change it. Very good. Thank you so much. So here, this is 100, and here 1000.
If you connect one cable, that works.
Yeah, yeah. That should work. So you can just you can select, and then you can move it to the left so that you can see. So we have 3 sinusoidal components. They are added together that make the input VI. And we have capacitor here, we have resistor. And I'm going to just rename it and call it simply R. And double click here and call it simply C. Okay. All right. Now save. Now I want to see the input and output of the same block. But before that, or I can place the marker right now, but now we are ready to simulate this circuit. So we are going to simulate this circuit using PSpice. So we click PSpice and then new simulation profile. Okay. So look, I'm going to keep a name for this simulation profile. So let's say, usually I give same name because the extension is going to be different. So RCLPM, create. Now I'm going to here analysis type. There are many analysis types. So I'm going to just simply choose time domain and run to time. So for how many seconds I want to run. So usually, let's say what is the highest frequency here?
Or 1,000 Hz.
1000 hertz. What is the time period?
It
1000 hertz is
Wow.
1 millisecond, right?
yeah.
1 millisecond. So let's say 1 millisecond, let's say we run for 50 milliseconds. So 50 milliseconds is basically here 50 milliseconds is basically, you can write 50 milliseconds, or in terms of seconds you can write 0.05. And maximum time steps. So it is the sampling time. How smooth you want your output signal to be. It depends on the. It depends on the number you put right here. So I'm going to put a sampling time very small. So maybe 1 into the negative 4, for example. If you make it even smaller, it will take a long time to simulate. But that's a small enough sampling time. This is small enough to simulate it nicely. And I'm actually giving this number. It is. Do you see here TS? This is the sampling time, and the value of TS I'm giving right here. It is the value of TS. So okay. Now, I'm going to simulate. PSpice run. So it is going to show an output window as you see right here, and there is nothing here. Okay? It's black. Now, to see something, what we need to do, we need to add voltage marker here. So you go to PSpice, markers, voltage level, and I am going to put it right here. And another voltage marker right here, probe, these are probe actually. Escape. Do you see? Immediately you see the input and output. And what does it mean? So here, the green is this green, are you guys able to see? This green is the voltage across capacitor from terminal 1 with respect to ground. That's what it means, guys. So from terminal 1, that is why guys, I mentioned the terminal. The pin number is very important. That way you know where you are taking the voltage from, signal from. So this is, you are seeing the voltage of capacitor from terminal 1 with respect to ground. So from terminal 1 with respect to ground. And that's what it means. And you see this red signal is the voltage of V1, voltage of this terminal with respect to ground. Okay? So you can actually double click here, and you can add more components here, more variables here, and then you can change the width, for example, here, place property, and you can change the width, for example, color, and you can make width, keep it as it is, and then color, you can choose different color. Okay, I chose red here, but if you click on this trace, this signal, right click, trace property, you can choose a different color. So make it blue, for example. You like blue, guys? So blue, blue, and then pattern, you can make it dashed. I don't know, this one as well, doesn't matter, as long as you understand, and make it thick a little bit, okay? You see that? Yes, sir.
Can you go over how to get to that window and what tool it is?
Okay, so this window, what I did, I created a simulation profile here, a new simulation profile, and you give a name, choose analysis type, give all the parameters, and save. So here, PSpice, new simulation profile, give a name, and once you give a name, you will see this window. You will see this window, okay? Here, you choose analysis type, time domain, and runtime 0.05, and this is the sampling time. Sampling time shows very small, so that you can see the output signal nicely, and then click OK. And after that, simply hit run. You will not see anything, you will see blank screen. But if you want to see something, you have to use Pro. Okay? You have to use Pro. So this Pro in PSpice basically it is PSpice, markers, and voltage level. You can actually, it doesn't hurt me, you can add current as well. So for example, I want to see how much current flowing through this resistor. Okay? Immediately you will see there should be another. Do you see here? So current, you can see it's almost zero, but what you can do, you can have another window there. You can show current. So what you do, you say right click, add trace, and then we see IR. So I'm going to show current flowing through the resistor. Yeah, so this is the current flowing through the resistor. So current is also sinusoidal oscillator. You see that, right? So it's hard to see, right? I can make it big because it is computer, it's not. Okay, so here, trace property, and then make it, I don't know which color do you like. Make it this pink. Is it clear enough? It's better? All right. So that's how you do the simulation, guys. So I'm going to stop recording here. It's going to convert it to MP4. I'm going to post it. I think he was still.
I just wanted to see how to add the window,
Oh,
because we know how to add the trace, we just needed to know how to add the window.
so what you do is, so you go to plot, add plot to window. Okay?
Alright, thank you.
So I think recording will be stored in my computer. I'm going to post it. Okay. So this is how we get the time domain is.
So when I tried to plot I1, I got 0, even though my voltage graph was right.
Yeah, 0, you plot it in new window because the value of I is in the range of milliamps. And the voltage is in volt. Okay? So if you look at the scaling, yeah, you will see there are some values, but because of the scale factor, you don't see this physically. You plot it in new window.
There we go, okay.
You got it now?
Yes.
All right. So, guys, did you understand? So this plot and body diagram, body plot, you would be showing to the PA, and you can show it to me as well during the office hour, okay? So now let's go through a theory. So this is what we are expecting, okay? Now let's see how it is going. Do we have time, guys? We have time, right? Okay. So this is what we did, number 6. Now we go back to number 1. So derive the Laplace transfer function here, okay, of this circuit. Look, guys, what is the impedance of this resistor? CR is simply R. And what is the impedance of this capacitor? This impedance GC equals 1 over SC, right? So now you can simply use a voltage division principle. So let's put this in frequency domain. So this is time domain. In frequency domain, we have this input VIS, and in frequency domain, we have this output V0 of S. Okay, so now number 1 solution. Using voltage division principle, V0 of S is simply voltage across the capacitor, which is the voltage across the capacitor, which is GC over ZR plus GC times VIS. Simple voltage division. And that's the beauty of frequency domain. Simple voltage division principle. But you will have to convert all the components in frequency domain. So now V0 of S over Vi of S is your transfer function of your filter, which is G of S, and some book I'm going to denote G of S, but in the book author has mentioned T of S, which is same, okay, which is basically GC, which is 1 over SC over R plus 1 over SC. So your transfer function T of S is simply 1 over 1 plus RCS. So this is the transfer function. Next, find the frequency transfer function in terms of physical frequency H of S. Again, number 2, author has actually denoted it with T of omega. So you substitute S equals, we are dealing with sinusoidal signal, guys. We are dealing with sinusoidal signal. So therefore S equals simply J omega, not the real part. We will not be dealing with real part because the input is sinusoidal, steady state sinusoidal signal. So which is S equals J omega and omega equals 2 pi m. If you substitute S equals J omega, it is going to be function of omega. Okay? I'm not going to write down T omega, you can write down T omega. So T omega is going to be 1 plus 1 over 1 plus J RC omega. This is your T omega. But if you write in terms of my notation, frequency transfer function in terms of physical frequency, so H of F is simply, you just substitute omega equals 2 pi, which is 1 over 1 plus J 2 pi F RC. Okay, guys. Now output, so this is not part of the answer. The output V naught of F is simply H of F times Vi of F. Look, when F equals 0, what does that mean? F equals 0. What does that mean? F equals 0. When F equals 0, what does that mean? What sort of signal it is? Frequency is 0. What sort of signal it is? DC signal, right? Right? If F equals 0, which means the input signal is DC. If F equals 0, input signal is DC. So what is the value of H of F? 1 over 1 plus F equals 0. 0, which is simply 1. Which means output is same as the input. So input is going to be passed to the output. Is that clear, guys? So for DC input signal, output is same as the input. As you increase the frequency, you will see that output is going to be deteriorated. It will deteriorate, right? Okay. When F equals infinity, means very, very high frequency. What is the output? When F is infinity. So something over infinity, as this becomes infinity, something over infinity is going to be 0, right? 0, and 0 times input is 0. So high frequency component is going to be simply executed, will not pass at all. Okay? So high frequency signal will not be passed. That's why this circuit is called low pass filter. That means it is passing low frequency signal and it is actually discarding all high frequency components. So, and this is called the frequency transfer function, according to my definition. And then determine the half power frequency FB, half power frequency FB. Guys, please pay attention why it is called half power frequency. Half power frequency means the frequency at which the output power delivered to the output, which is V across the capacitor. Power delivered to the output is half of the input power at that frequency. So power delivered to the output is going to be half of the input power at that frequency. So that's why frequency, that frequency is called half power frequency. Also people call it corner frequency, people call it break frequency, people call it 3 dB frequency. There are many names. Okay? 3 dB frequency means in terms of decibel, the gain is going to be 3 dB less than the initial gain. That's why it is called 3 dB frequency. And half power frequency again, the output power at that frequency is going to be a half of the input power. All right. So number 3. Number 3, you can write H of F is 1 over 1 plus J F over F. You can write it like that. And FB, where FB is 1 over 2 pi RC. This is the half power frequency or break frequency or corner frequency. And you will see after this frequency, you will see that output is going to deteriorate. All right. So this is the break frequency. And then plot the magnitude and phase of H of F. And this is basically the frequency response. When you plot magnitude and phase of H of F, it's called frequency response. It's called frequency response. And I am going to, so it's a complex function, right? 1 over 1 plus J 2 pi F RC. Now you go back to the background. information where I talk about complex frequency, how to deal with it. You will see the magnitude, it's number 4, right? So magnitude of h of f is going to be 1 over square root over 1 plus f over f squared. And that is the magnitude. And magnitude in terms of dB, h of f, magnitude in terms of dB is 20 log 10 h of f. This one. Oh, by the way, guys, you see, I actually plotted it using LaTeX, the language that I use to produce my notes, and using MATLAB as well. Do you see that? It's very similar to what we got using OrCAD PSpice. Okay, so we have the magnitude and phase h of f, and we denote it with as such. So it is going to be magnitude of phase of 1 minus phase of 1 plus j f over f. So phase of 1 is going to be 0 minus the phase of this quantity is going to be a tan 2 f over fp, comma 1. And you can actually convert this in degree, which is negative 180 over pi a tan 2 f over fp, comma 1. And that is going to be in degrees. Okay? So when you plot the magnitude and magnitude in dB, and when you plot magnitude of the frequency response in dB and angle, which is phase in magnitude in dB and phase in degree, then these two plots are called body plots. These two plots are called body plots or body diagram. So in other words, you will see that this is h of f in dB, and this is frequency, and then we have frequency, and then we have phase, h of f, phase in degree. Okay? So you will see plot like that. You will see plot like that. And you can use MATLAB to plot. And what I would like to do, I would like to see these plots, these body plots, using OrCAD PSpice as well. But for that, what you will need to do, you will need to use SC sweep. Make sure you choose SC sweep, and then SC sweep simulation analysis type SC sweep. And I'm going to show you in a moment if I have time. And these two are called body plots. Next, what is next? Number 5, right? So if the input is simply A cosine omega t plus B sine omega t, in general, the output is going to be output. I'm going to directly write the output is going to be square root over a squared plus b squared, then magnitude of so you have whatever you have magnitude, not in dB, magnitude of this frequency transfer function, and then cosine of same frequency plus 5 plus 5h, where 5 is tan inverse B over A, and 5h is basically the phase of your frequency transfer function. So this is number 5, and number 6 we have already done this. Okay? So we have 1 minute. Now I have a question to you guys. Right after this class, what class here? Right after this one, can I borrow just maximum 10 minutes?
I feel bad after this.
Okay, forget about it. All right. So in that case, we'll continue next week. I'm going to stop right here. Now, what I would like to announce, because I have a minute. Next Thursday, we will have a quiz, 10 to 15 minutes quiz. Quiz is going to be based on what we covered. Go through the examples. The tips is go through the examples that we went through, and related examples from end of chapter of the book. Exercise that I mentioned, practice that. You should be in good shape. That's all. The tips for the quiz. It is going to be maximum 15 minutes quiz. Maximum. One problem, some 1 or 2 possible questions. Clear? And quiz is going to be towards the end of the lecture. Any question? No? All right, thank you. I will see you tomorrow. On Thursday. It's in the schedule.
See you later.